Hello, ladies and gentlemen. I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one's entitled Unbelievable Size and Speed of Planet X. Now, in Article 596, entitled The Wormwood Star, I detailed how a star, which I call the Wormwood Star, is responsible for the poisoning of 1/3 of the Earth's fresh water supply. Since the Planet X objects or stellar cores which have been observed within the Earth's atmosphere have been small in size, where some seem to only be 250 feet in diameter, it is surprising that a Planet X star, which would have to be many times larger than the Earth, would come to Earth and cause this cataclysmic event. So how large can the objects that come to Earth be? And here you see some of the objects that have been observed inside the Earth's atmosphere. You can see this one that's starting to lose its cloud envelope. And you can see this one, you can see its cloud envelope there. At first it looks like a break in the clouds, but you can see that the surface here is convex. In other words, it curves downwards. This is the underside of a spherical object, and this would be its south pole, which is not covered in cloud envelope. And you can see the cloud is emitting pink, gray light, and the surface of the object itself is emitting this pale blue light. Now here we see another one. If we look carefully at this looks like the crescent, the moon's crescent. But if you follow the outline of the circle, you can see that it doesn't coincide with that one. So you actually have the crescent of the moon superimposed on a spherical object. And you can see it's not black, it seems to be gray. So it's most likely covered in its cloud envelope as well. And from the size of the moon hologram, because this would have been a hologram, I have estimated it to be about 250 feet in diameter. And you may look at Article 547, entitled Planet X covered up by the moon hologram in the Earth's atmosphere, for more details. So there is actually no upper limit on the size of Planet X objects which can come to Earth, just like there is no upper limit to the sizes of the objects that can go to the Sun. All they have to have is an average nucleon. A nucleon means a proton or a neutron. It encompasses both particles. So the same average nucleon density, which is the same or higher than the Earth's average nucleon density in the case of Earth, and the same or higher than the Sun's in the case of the Sun. Nucleon density is the number of nucleons per unit volume. Neutrons are included because a neutron is a proton combined with an electron. The average nucleon density determines the gravitational energy level of a celestial object. In each celestial object, there are layers at different nucleon densities. Matter of higher density will also be higher nucleon density. The denser layers are closest to the center of the object, and the least dense are in the atmosphere. At the very center of each living celestial object, there will be a layer that will be at the maximum density available in the universe, a piece of plasma which originated in the original supercore, from which all celestial objects eventually formed. This piece of plasma is what keeps celestial objects from colliding with each other. And you may look at Book 10, entitled Planet X Reveals How the Universe Works, for more details. The nucleon density determines the energy level of a celestial object because protons are the particles which interact through the attractive part of the gravitational interaction, which is also known as the strong nuclear force. And this is illustrated by this interaction, the attractive force between two protons. And of course it encompasses neutrons, because even when a proton and an electron are combined to create a neutron, there's still a proton in there which feels the same attractive force for other protons. And this is the electrostatic interaction, which operates in the opposite way. The two always oppose each other. You can see two protons here repel each other according to the electrostatic interaction, but according to the gravitational interaction, they attract. This is what actually leads to gravitational attraction. And protons and electrons repel, which is opposite to what occurs in the electrostatic interaction. And this I call the charge separation interaction, and what leads to all matter in the universe having an outside negative layer. All planets, all stars, all galactic nuclei, they all have an outside negative layer. And so do atoms. Now, objects which have a lower average nucleon density than the Earth will not be able to get past Earth's orbit once inside the solar system, and will thus go to planets further out from the Sun in the solar system, such as Mars. Debris pieces which have a lower nucleon density than Earth's average nucleon density will thus end up in orbits further out from the Sun, such as the one which referred to as the asteroid belt. Since debris pieces are likely to be less dense than the stellar core they belong to, debris pieces cannot get past the solar system orbit that the core cannot get past. Outer pieces in the debris field, which tend to be closer to having a neutral charge, will also remain further back in the solar system as the remaining debris field and core continues deeper into the solar system. And here you see some of these objects in the Sun's corona. You can see this one turned out to be about 4 times the size of the Sun. You can see it's striped. You can see the curvature in the stripes because they're following the curvature of the surface of a spherical object. And this is an object that has most likely absorbed quite a lot of material from the Sun's corona. So it's got clouds on it, somewhat like Jupiter, because Jupiter went through this same process. And here you see another one. This one's about half the size of the Sun. So stellar cores 4 times the size of the Earth, like this one, is likely to be the lowest size limit on objects that had operated the stars as living celestial objects, although there are actually very few differences between planets and stars. And this is because we expect only objects that were once stars to actually make it all the way to the Sun. Since the larger stellar cores would have been cores of larger objects, and since larger objects would tend to be stars, while smaller objects will tend to be planets and even smaller moons, it is likely that only star cores get to the Sun. The stellar cores that have been observed in the Sun's corona have ranged in size from about 4 times the size of the Earth to many times the size of the Sun. So it is likely that objects smaller than that have too low a nucleon density to reach the Sun. Debris pieces which reach the Sun would most likely be a part of the larger stellar core and are most likely also from the inner part of the debris field and thus denser than the pieces in the outer part of the debris field. Planet X debris, especially surface debris pieces such as the ones that have buildings on them, and you may look at Article 584 entitled Planet X, the Reason Behind GMO Crops for more details, which come to Earth would belong to stellar cores which are about as large as the Earth's core or larger, and may have thus belonged to a planet of about the same size as Earth or larger. Stellar cores will reach their maximum speed as they reach the perihelion position of their orbit. The perihelion position is dependent on their average nucleon density. The larger objects tend to have higher nucleon density and thus will reach further into the solar system and will thus also tend to reach higher speeds. But the speeds are dependent on the charge of the object, which is different from the nucleon density, as neutrons contribute to the nucleon density, but not to the charge of the object. However, the higher the nucleon density, the higher should the charge of a stellar core be, with nucleon density always being higher, which still means that larger objects will reach higher speeds. And this is illustrated by this diagram where you see a large stellar core, and it has a higher nucleon density because it's larger, so it's most likely was a star as a living celestial object, has an orbit with a perihelion position that gets very close to the sun. It doesn't quite go into the sun, so it may have a nucleon density that's slightly less than the sun's average nucleon density. But it still gets very close, and it will be moving at its fastest when it's at this position. So it will also be moving much faster than this object, a small stellar core that cannot even get close to the sun. It just crosses Earth's orbit here. And this one will be moving at its fastest in this position, but that speed will be much lower than this one's speed in this position. And you may look at Article 577 entitled Planet X Created the Asteroid Belt and Rocks in the Sky for more details. So larger stellar cores will have perihelion positions at which point they will be moving at the fastest speed, much closer to the sun, and will thus be moving much faster at perihelion than smaller stellar cores. However, nucleon density translates into mass density, as almost all the mass of an object comes from the protons it is made of. Thus, the ratio of charge density to nucleon density is equal to the charge to mass ratio. Therefore, all the stellar cores, since they are not expected to have any electrons except for the ones which combined with protons to make up a neutron when they arrive in the solar system, and if they manage to cross Earth's orbit, will be moving at about the same speed. And to see this, we can apply Newton's second law along the radial direction, where we have the electrostatic force, which is the electrostatic constant, the charge of the sun, the charge of the object, and this is the distance between the object and the sun. So we want to know at Earth's orbit, this will be 1 AU, the distance between the sun and the Earth. And then the other term, the gravitational term, which has the gravitational constant g, the mass of the sun, the mass of the object, and again the distance. And that's equal to mass times acceleration, and the object's moving in an orbit. So the acceleration is the speed squared divided by the radius of the orbit. So the gravitational constant is dependent on energy. But so it would be very low for these objects, the stellar cores. But from this equation, let's first find what the speed is, and we just solve for the speed squared here, and this is what we get: k capital Q over little q divided by mr plus g capital M over little r. Remember, we cancel one of the r's here, so we end up with only one r in the denominator. And then we divide by m, so that goes, and then we need an m in the denominator there. Now, but as I said, this g is very small for these objects because they are extremely depleted in energy, and that means that we can basically leave out this term, and we only left with the electrostatic term. And that electrostatic term tells us that the velocity squared, or the speed squared, is proportional to the charge divided by the mass of the object. So that's the charge to mass ratio, which tells us that since the charge to mass ratio, the Q over M, is expected to be constant for all stellar cores, they will all be moving at the same speed when they cross Earth's orbit. And the fact that the charge to mass ratio remains constant, well, that is illustrated here. So we have matter, which this represents matter in a small stellar core, and what we have is, these are protons and these are neutrons. So here we have 6 protons and 3 neutrons. The protons and the neutrons have just about the same mass, very small difference. So I've given the mass of each of these the value capital M. So there are 9 of these here, so we have a total mass M for this sample of matter for a small stellar core of 9 capital M. And the charge is, only the protons have charge, the neutrons have 0 charge, so the total charge is 6 times E when each has a charge E. So there's 6 of these, 6 red ones. Now for a large stellar core, it will be denser. So it will have a denser nucleon density, which means that a sample of the same size will have many more nucleons. Remember, nucleon is a proton or a neutron. They're both nucleons. But what we have here is many more. We have 18 nucleons now. So the total mass of the sample is 18 times capital M. And we have 6 neutrons. So the total number of charges is 12 for the 12 protons. So we have the total charge for the sample of 12e. So then we can calculate the charge to mass ratio for both, and for this one it's 6e over 9m, that's 2/3 e over m, and for a large one it's 12e over 18m, and if we divide top and bottom by 6, we get 2 over 3, same ratio. So the ratio is not expected to change. Now debris pieces, so if it doesn't change, remember, it's the same for all sizes, the Q over M, so they will all be moving at about the same speed when across Earth's orbit. Now, debris pieces will have a mass to charge ratio which can only be lower than the stellar cores, as they will be less dense in terms of nucleons and may have electrons in them, which will further decrease their overall positive charge. Surface pieces may be close to neutral because they will most likely have a lot of electrons which were absorbed from the atmosphere as the planet broke into pieces. So these pieces will be moving at much slower speeds. However, they will come in as part of a stellar core's debris field and thus come in at the same speed as the stellar core. So even those close to neutral pieces will cross Earth's orbit at the same speed as the stellar core. Its electrons will move to the stellar core side of the object, thus making it positively charged on the outside. But since the electrostatic force between all the pieces is repulsive, there must be another force which keeps the core and debris pieces together, which must be attractive and thus gravitational in nature. Since they are so low in gravitational energy, it must be the mass part of the gravitational energy that keeps all the pieces together. And since this force does not manifest between stellar cores and solar system objects, this force must only exist between created matter and the parent core. This is the reason why solar system planets, which were created out of solar material by the sun, will always remain connected to the sun. Debris pieces in the form of asteroids or meteors will cross Earth's orbit at different speeds. The ones with the highest charge to mass ratio will have the highest speeds, but since their charge to mass ratio will never be as high as the stellar cores, they will always move slower than stellar cores as they cross Earth's orbit. So from their speed as they enter the Earth's atmosphere, we can get an idea of how fast the stellar cores are moving past Earth's orbit. The fastest asteroid on record was the Sutter's Hill asteroid, which entered the atmosphere in April of 2012. And it was moving at 68,000 miles per hour, which is 103,000 kilometers per hour, or about 30 kilometers per second. And since this is about the same as the Earth's orbital speed, the object would have had to be moving at a speed of something like twice the Earth's orbital speed with respect to the Sun, at about 60 kilometers per second. Planet X system stellar cores will be moving much faster than that, so they must be extremely fast-moving objects until they enter the Sun's corona, where the forces acting on them completely change, and they may then remain stationary with respect to the Sun for extended periods of time. Debris pieces which get torn away from their parent stellar core will go into the appropriate orbit for their density. So in conclusion, Planet X system stellar cores coming to the Earth have no size upper limit, and therefore there is no upper limit as to the size of the wormwood star, which the Bible tells us will come to the Earth and deeply affect it. But since it is the core of a star, it will most likely be at least 4 times larger than the Earth. These objects are extremely fast-moving with speeds greater than 60,000 meters per second as they cross Earth's orbit. The fact that the Wormwood star affects Earth in several ways suggests that it does not just pass by Earth. It actually comes to Earth to absorb energy from it, like many other Planet X system stellar cores. And these are the references. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.